Hi, today is 6th January 2026. This is the third episode of my YouTube channel. Today I'm going to discuss a completely technical thing about electrical engineering. So today I'll discuss how transformers are operated and maintained. Basically operation and maintenance of large power transformers. I think there are a lot of YouTube's channel for transformer design, how to size, also even operation and maintenance. But I think I had a huge number of years I spent in transformer operation and maintenance, and also design. So I thought I will discuss some of those. So transformer design is nowadays pretty easy. Like there's thousands of vendors all over the world. They design and manufacture transformers. But obviously there are good or bad. Like if you talk about a company like ABB, they produce one of the best transformers. Of course, there are many other companies like ABB. So many people think that okay, transformer is very easy. Of course, it is static equipment. So the one side is high voltage, one side is low voltage, and there's a core inside, and there are high voltage and low voltage winding, and it's cooled by oil most of the time. So it is not difficult, and we see transformer everywhere nowadays, even small transformer in our household equipment. And if you see the printed circuit board, they have a small transformers are everywhere. So electrical design is pretty easy. It is like transformer depends upon the trans ratio, like the V1 by V2 equals to N2 by N1, and the voltage generated is a EMF, E equals to 4.44 phi Fn. That I think that is proportional to. So that is, I think, almost everybody know all electrical engineer basics. Those who are electrical engineer, of course. So, but during the design, I have been to many big factories, and I found that electrical design is not that difficult. But what makes a transformer last longer is the mechanical design. A lot of people do not pay attention to mechanical design, the smaller vendors, and those transformers fail early. If you think about how the transformer works, it is basically one side is high voltage, one side is low voltage. Basically, the low voltage side current is more, so that current produces a lot of heat, and heat has to be dissipated. And I'm discussing today mainly the oil immersed transformer. I'm not discussing air transformer or SF6 cool transformer. Those can be a separate discussion. But basically, oil transformer, the oil has to cool the transformer, and to design the oil circulation passage, clearances, radiators, that is very critical. And if you see transformer failure, like a electricity board transformer fail suddenly on the pole, those are mostly from the mechanical design issues. So the mechanical design, basically what? Mechanical design means the cooling oil has to circulate and take out the heat from the windings and go to the radiator or the body and cool it back if it is a natural cooling. If it is a forced cooling, there are fan on the radiators or even the water circulation pipes around the radiators for very large transformers. And there could be oil pump also, but I'm talking about the standard transformer, which is say up to say 10 MVA, 40 MVA, 50 MVA, 60 MVA oil immersed transformers, where the radiator can cool it with one rating. So the transformer rating I discussed briefly. Transformer rating is basically describes in MVA. I think electrical engineer knows that. So the cooling, actually you can have a forced cooling to enhance the power rating. Let us say a transformer is 10 MVA, 11 kV by 400 volts. If you can make it 12.5 MVA by putting some fans cooling. There are two sets of standard. One is IEC standard, which is the European and Asia Pacific, and there's North American standard. IEC standards are normally, if they design the cooling with 25% more capacity most of the time, either 25%, and then if you do second type cooling, there's 50% more. Like say 10 MVA transformer could be 10 MVA, 10 12.5 MVA and 15 MVA. Whereas in USA, they design slightly differently. US, they normally do 133%, 166%. So basically a 10 MVA, say a 10 MVA transformer will be like 13 MVA transformer or 16 MVA transformer, 10, 13, 16. Or if I take it a 100 MVA transformer, it will be 100 MVA, 133 MVA, 166 MVA. Whereas in European design, normally it is 100 MVA, 125 MVA, 150 MVA. That is, it can be changed also nowadays, because nowadays all computer design. Earlier it is a manual design, so manual they used to keep some margin and other thing, but nowadays computer design. And when I talk about computer design, because of computer design, computer aided design, the transformer design become very tight like any other instrument. So the margin is very, very low. So if it is not operated properly, it will fail faster. I just give you one example. If you take a very old transformer, like if you find a very old transformer, find out how much oil inside it and what is the kVA. If you do the kVA to oil ratio, you will find, let us say, I'm just giving example, it's not exact figure. Let us say 10 MVA transformer, let us say it could be a 10 MVA transformer could have 12,000 liter of oil, let us say standard ONN transformer, very old design. If you take a modern 10 MVA transformer, it could have only 8,000 liter of oil. So it is almost reverse. Earlier the oil was much more compared to what we have now, because the computer design, it still works. It's not that it doesn't work. The life become less. That is the only difference. So when you buy a transformer, don't just concentrate on your electrical design. Also check with vendor about the mechanical design and specify correctly what is the temperature, ambient temperature, what will be temperature rise, and how much transformer will be actually loaded. Because the vendors sometimes think, okay, he's buying a 16 MVA transformer, maybe full load is not 16 MVA. So that's why you should insist on a heat run test. Because a lot of people don't do heat run test because it is cost, additional cost. But if your transformer you think will be loaded fully most of the time, you should insist for a heat run test during purchasing. Because heat run test will actually tell you the temperature rising up to certain limit, and then it is working fine. So oil immersed transformer insulation class is normally class A. So if you are electrical engineer, you know that there are various type of insulation class, Y, A, E, B, F, H, C. So class A is approximately 105 degrees Celsius maximum. It's a paper insulation. So the ambient temperature is normally considered between 35 to 40, and the temperature rise, let us say 60 degree. So 40 plus 60 is 100. So maximum temperature transformer will take 100. So if this is exceeded, then the transformer life will come down. That's basic, very simple. All electrical equipment are mostly heat dissipation, because conductor is copper conductor. Copper is not going to fail. The heat has to dissipate somewhere. See, if the heat is dissipated through insulation, and the insulation is heated up, then for motor, etc., there will be partial discharge and other thing, that will be failure. For transformer, it is basically a paper insulation. Paper will degrade over time and fail. If the heat is not dissipated, paper will be hot, there will be hot spot, and that is the first place it will fail, then it start failing. That is the bottom line. The voltage is not a big issue. Even if we call it a very high voltage transformer, low voltage transformer, the turn to turn ratio of winding is not very high. Even if you have a, let us say, 132 kV primary voltage versus 11 kV primary voltage, the way the transformer is designed, the high voltage winding or even low voltage winding, the turn to turn voltage between the two winding is between 40 to 60 volt. That's it. It cannot be more than that. So that paper is good enough for that. So that is not the issue normally. The issue is the hot spot, and then the paper fail, or dust and dirt, then it becomes short. That is the starting of failure. So that is one thing one has to remember. So another thing also, remember that the temperature and insulation has got a very clear log ratio. So every 10 degree temperature, if the insulation is designed for a particular temperature, every 10 degree rise of temperature, the life will be half. So it's like this. So normally, from a good vendor, reputed vendor, a oil image transformer should easily last 25-30 years if the load is, say, not more than 90% of the rated load, and if you have done the heat run test, means basically transformer designed correctly. But many times the transformers are very lightly loaded. Like in a industry, we always have a standby transformer, backup transformer. For a continuous process industry, I came from a oil and gas industry. Because it is continuously process industry, so we always have two transformer running in parallel. So not always parallel, but two transformer feeding the same switchboard. So basically each transformer is half loaded. Because it is half loaded, so the temperature rise is very low, and the transformer can easily last 30, 40, 50 years. Even I have seen 60 years transformer operating. But if you have a transformer, only one transformer feeding the load, and the load is 70-80%, sometimes let us say captive transformer, like generator captive transformer or motor captive transformer, most of the time the transformer is 70 to 80% loaded. So those transformer life will be obviously low. I will say like a good design transformer will be between 20 to 25 years. And what is the failure mode? Failure mode is that if somebody is not maintaining the transformer, not cleaning, etc., the failure mode is basically a hotspot in the winding, and that is the starting of failure. So this all come back to mechanical design. Electrically, as I said, the copper doesn't fail. The two more vulnerable thing inside the transformer electrical is the off circuit tap changer or the on load tap changer. These two are there is a cleats and it moves the winding. You can change the winding. So this is the only moving part inside the transformer. So that is a one vulnerability which can fail if the cleat is not designed correctly, or after long years nobody move it, and then while moving it fail, or if it is moved too frequently, that is also another chance of failure. And because it is clit, so a lot of connection there. There are normally off circuit tap changer, there will be 5 taps, so there are 5 connections. For OLTC there are 20-25 taps, so there will be 20-25 connections, so those are vulnerable. The second weak point in the transformer is the bushing, which is outside. If the bushing is not properly taken care of, the creepage distance, and if it's oil fill bushing, the oil level goes down, then also it will fail. So electrically there are very few things to fail. So mechanical design is not correct, then the transformer will be heated up and hotspot will fail. So what is the ideal transformer rise temperature? Ideal transformer rise temperature is between 55 degree to 65 degree, not more than that actually. So as I said, ambient is 45 or 40, so 40 times 60 is 100 degree, that is your maximum. So now, how do we maintain it? So oil image transformer has a fantastic opportunity to review the health of the transformer by testing the oil. Very easy. So oil can be tested two ways. One is we call it a oil analysis. Oil analysis basically how much moisture is in the oil, what is the oil dielectric capacity of the oil, what is the acid number in the oil, what is the surface tension of the oil. This gives a lot of data. The second test is there any dissolved gas inside the oil, like hydrogen, methane, ethane, acetylene. This gives another set of data. From there you can predict when the transformer will fail, or how long the transformer will going to last. From where the dissolved gas coming? The dissolved gas coming from the paper. Basically paper is degrading, and if there is a hot spot, the heat will produce carbon dioxide, carbon monoxide, hydrogen, basically hydrogen. So basically hydrogen, carbon dioxide, carbon monoxide, methane, ethane, ethylene, that gives you a very good idea about what is happening inside the transformer. So the detection to failure in transformer, like we call it P2F in reliability, is quite long. So suppose if you do a regular good test of oil, and if you detect something, and it's not going to fail tomorrow. So the P2F, the failure may be 1 or 2 years away. So if you do once a year oil test, that is good enough. That's good enough. And how to interpret the oil? There are the many standard how to interpret the oil. The most widely used in the world is the IEEE C57 standard. So IEEE 357 standard dot it is called IEEE C57.104 and .106. IEEE 57.106. These two transformer gives a acceptable value, what to do, and what to look for, what to change. So these two standard, if you refer, that gives you a clearly good idea how to do with the transformer. The one thing we need to remember, the dissolved gas analysis, if there is a gas inside the oil, and people normally what they do, they change the oil. Okay, change the oil will help, because there are two things you need to understand this. One is the oil quality is degrading from the moisture or substantiation or the dielectric properties. That is, the oil quality is degrading because the oil, everything has got a finite life, because transformer is there for 20-30 years and is getting heated up, so oil can degrade. If the oil quality is degrading, you can change the oil. The transformer will again start behaving correctly. But if there's a dissolved gas, even if you change the oil, the dissolved gas is coming from the hot spot or winding paper or somewhere. So that is not going to help. It will help initially. The first reading will say, okay, everything is good, but after some time, immediately it will come back. Within 1 or 2 years, it will come back again, all the gases. And then you lose your earlier data. Let us say, I give an example. Let's say 1000 ppm total dissolved gas is bad. And now you see, say 500, 600, okay? So you change the oil. So now the dissolved gas showing only 400, 500 again, 300, 400. So you think it is good. It's not good, because already 500 oil has been changed. So you have to be careful about, if there's a dissolved gas analysis data is bad, and you are changing the oil, you need to keep the old data. It's very important. You would add those things into this. Not exactly add, but that is we can have a separate discussion. How to interpret oil is a very big subject. So that we can have another half an hour session on that. So today's discussion, I want to say that the mechanical design is more important than electrical design. Electrical, there are three vulnerability. Of course, the paper insulation, that is can be the health of the paper insulation can be checked by oil analysis. The bushings need to be maintained regularly, and the off-circuit tap changer or on-load tap changer, those nothing can be done, but those are vulnerable. So on-load tap changer, there is a modern improvement, because there are some vendor like MR and ABB started coming up with a vacuum on-load tap changer. If you buy a new transformer, you can opt for a vacuum on-load tap changer. Then the life is same as transformer. You don't have to do any maintenance, because the why the on-load tap changer degrade the transformer oil. Basically, when the voltage is changed from one contact to another contact, it will produce some arcing. Even if there is a shorting resistor, it will produce a minor arcing. The contact will become burned. From that is a failure mode. In vacuum OLTC, it is done by a vacuum bottle. So no arcing, no nothing. So new transformer, suggest buy OLTC. Large transformer, if you are buying OLTC, suggest buy a vacuum OLTC. Old transformer, when you replace the OLTC, if you replace the OLTC, I think it will be a good investment. Put a vacuum OLTC instead of, because OLTC need to be served every 7-8 years. Normal rule is every 50,000 operation, or 5 to 7 years, whichever comes earlier. So basically, for a large transformer with OLTC, you are maintaining every 5-6 years OLTC. And there are very few guys can maintain those OLTC. Their charge is very high. So by the time they maintain your OLTC 2 times, it is almost cost of your OLTC, or 3 times. So if you put your next maintenance, if you put a vacuum OLTC, then I think you don't have to do any more maintenance. So that is one thing you can try actually. So the operation, what you have to do, operation basically you have to check the temperature. That's it. So all transformer comes with at least one or two temperature indicator, oil temperature indicator or running temperature indicator. Of course, you have to check the level. Level is very important. Oil level has to be there. There could be leak or something like this. So you check temperature regularly, say once a month or once in 3 months. As long as the temperature rise is within 60 degree, you are good. Okay. If the temperature rise is more than 60 degree, means from your ambient, no matter what is the ambient. If your ambient is 40, also it is 60 degree. If your ambient is 20, also it is 60 degree. Why? Because it is not that your winding is going to fail. Because if your ambient is 20 and temperature is 60 degree, 80 degree, you still have some margin. But if your transformer is heating up 60 degree, that means it is operating near the design. So probability of hotspot etc. is always there because they enclosed space. So it is some people think, okay, I am in a Middle East, say 50 degrees Celsius, and 50 degree temperature rise there become 100. That is much more dangerous than operating in, say, Northern Europe where the ambient is only 25 and I can have 70, 80 degree temperature rise, which is not exactly correct. You can have more temperature rise because not exceeding the insulation limit, but inside your transformer the hotspot will be more. That is, then the transformer is not operating correctly. Okay, so that is the thing. So check your oil temperature, check your running temperature. As long as it is within 50-60 degree, you are good. Transformer loading, of course, you cannot have loading more than is designed, and oil level. These are the three things. And you do oil maintenance, oil level, and oil analysis. Two type of oil analysis, actually three types. I come to the third type. So first type is you take the oil, do the dielectric analysis, surface tension, acid number, and ppm. That gives you a very good idea about the oil quality. Second one is the dissolved gas analysis. It gives you the health of the transformer in general. Is there any hotspot, what kind of gas is coming out, and those kind of things. See, in the oil, you need to remember the moisture content is one of the very clear indication, and dielectric strength. Dielectric strength need to be, say, within the 40. It depends again. The IEEE gives a very, very high voltage. It should be maybe at least 60 kV. The breakdown voltage. For lower voltage, you can accept up to 50 kV or something like this. The moisture content is interesting thing. You need to be a bit careful on this. So moisture content, people say, okay, up to 30-40 ppm is acceptable. It is true, up to 30-40 ppm may be acceptable, but you have to play by the ear actually. So let us say a small transformer where you have 10,000 liter of oil. So 10,000 liter of oil, and oil test is 40 ppm. 40 ppm in 10,000 liter oil. Okay, so you know the water content. Now you have a very large transformer. Let's say that has got 30,000 liter of oil or 40,000 liter of oil. And if you have same 40 ppm, then 40 ppm of 40,000 liter, which is a very high of free water inside the transformer. So although the guidebook says, okay, between 30-40 ppm acceptable, but you have to take with a pinch of salt. So there, as I say, we can have another session to discuss how to interpret the oil. So if the oil ppm is high, you also need to check if the surface tension strength of the oil is good. That gives you another indication. Or the acid number is good. That gives you another indication. The second one is the dissolved gas analysis. So as I say, we will have another session how to interpret the dissolved gas analysis. The third one is also kind of a dissolved gas analysis. It is called degree of polymerization. There is a test called Furan test that basically tests the degree of polymerization of the paper. As the transformer become older and older and older, like 20, 30, 40 years, at one point of time, your paper, all the cellulose of the paper is gone basically because of the continuous circulation, heat, etc. So paper will become like a plastic. You might have seen in your home also, you put suppose you have keep your paper on an oily surface, the paper become oily. You keep that thing for a very long time, it become like a brittle, plasticky. It will same thing inside the transformer. So if the paper become very, very old, basically the paper will start losing the cellulose and the paper will become plasticky, and then it become brittle, and obviously if the paper is brittle, it is turn fault. Okay, so that is again the start of failure. So how to check that? That is called Furan test. This is one scientist basically developed. His name is Furan, I forgot. Okay, so the degree of polymerization, the base is 1000. Then every year after, normally Furan test you should not do first 10 years of transformer operation, because the paper cellulose is not going to go bad so quickly actually. Okay, so normally you start doing the Furan test, let us say from 10th year onwards, because it is basically checking your paper is getting plasticky or not. So the base is 1000, the DP. So if the DP is coming down 600, 500, 400, then you start checking more and more other dissolved gas analysis. But once the DP is below 300 or 250, transformer is going to fail. So it is time to change the transformer if you don't want to wait for failure. So operation is very simple. You look only at the temperature, look your no leak, the fans are working, if there is a cooling fans are working correctly, and the transformer is not loaded beyond its capacity, the bushings are good, OLTC is operating correctly, OLTC maintenance is done, and basically look at the temperature. That's it. If the temperature is good, you are good, and do oil analysis every year or every 2 years. Initially you should do every 2 years, but after the transformer become 10 years old, you should start doing every year. And the oil analysis gives you a fairly good idea what is happening. If the oil quality is getting bad from the oil analysis, change the oil. If the winding quality is going bad because the hot spot, other thing, from the dissolved gas analysis, then you need to think something else. The IEEE, as I told you, it has got a 4 level 1, level 2, level 3, level 4. So you can do a risk analysis when exactly you are going to replace the transformer, because you cannot repair that. If you have a hot spot and continuously generating hydrogen or carbon monoxide and carbon dioxide or total dissolved gas, you cannot repair it. You change the oil, it will come back within few years. So you have to change the transformer. When to change the transformer? Because a lot of capital investment, that is the risk analysis you do from the IEEE guideline, level 1, level 2, level 3, level 4. I will discuss that in another session, how to interpret the oil. What else I want to discuss here? Let me check my notes. So another thing I forgot to tell in the design, the transformer, because of the oil will expand when it is heated up. So they give some, there is a conservator, So conservator, actually oil expand to the conservator. And nowadays also available seal transformer. The seal transformer is basically there is a nitrogen gas layer. And if this is not seal transformer, there is a conservator, there is a silica gel breather. The silica gel breather also you need to witness, because silica gel breather is basically the air is going in and that air has got moisture, the silica gel color change, then you need to change the silica gel bead. But nowadays they put a rubber bag inside the conservator. So basically then your silica gel breather is not doing much thing. So technically it is a hermetically sealed transformer, because it has got a rubber bag inside the conservator, so oil is not in directly touch with the ambient air. The expansion is taking place, the rubber bag is getting expanded and contracted, so the silica gel breather you see outside, it is not really in direct, that air is not going inside the bag, rubber bag, so it is not directly in touch of oil. So silica gel breather is not a big issue if it is a hermetically sealed transformer. But if it is not a hermetically sealed transformer, yes, you have to do it. You have to change the silica gel bead once the color changes. What else? Quality maintenance we discussed, and then oil sample also we discussed. So another thing, as I say, like the other vulnerability is the bushing. There are another vulnerability that is not exactly the transformer part. This is a cable connection, because the cable connection comes through the primary and secondary boxes, and sometimes there's a bus duct. Those also could be weak point. If your connection is loose, even cable can failure. If the cable failure, it is not a transformer failure, but it will damage the transformer. So every 5, 6, 10 years, when there is opportunity, one should open the box, primary box and secondary box. If it's a bus duct, you check all the connection inside, tightening everything, clean the bushings. That is also part of we call it a 5-yearly maintenance. Another 5-yearly maintenance is the transformer has got a lot of alarms and from the protection city current transformers. It has got a marshalling box. All your winding temperature, oil temperature that gives alarm, it comes to the marshalling box, and the transformer protection current transformer also comes to the marshalling box. Those marshalling box the wiring need to be tightened once a 5 years. That is, I will say, another. So you check the power connection, you check all the marshalling box connection, you check the bushings in the 5 years, check for any corona discharge, and many transformer grounding is the medium voltage transformer grounding can be done through a neutral grounding register. You check the neutral grounding register if it is mounted on the transformer. If it is mounted separately, you check that separately, and that's about it. And OLTC, as I told you, the OLTC maintenance is a very interesting thing by expert. So go for vacuum type OLTC. That's all for today. If you have any question, you can post. I'll try to reply. Next session or some other time, I will do the how to interpret the oil analysis. As I say, it is basically IEEE C57.104 and 106. But I will add some of the other experience that I have, what I have seen, what to do. Let us say your total gas is this much. Am I going to change the transformer tomorrow or after 1 year? How to do this analysis? We can discuss that. And if you have any comment here, if I make any mistake, if somebody pointed out, I will try to correct that, or I will discuss that also next week. As I said in my first episode, I'm not going to edit anything. I will not add or delete anything. So if I made a mistake, please point it out. I'm not going to cut that part, but I'll correct that in my next episode. Thank you. Have a good day.